In this screencast, we're going to use humidity charts to help us model a heating process. Humidity charts are a graphical display of physical property for an air-water vapor mixture. For those of you that are using Felder and Rousseau as a resource, we can get a humidity chart in SI units from figure 841. The physical property data that we'll use for this problem include specific enthalpy and humid volume. Both of these are given to us on a per kilogram of dry air basis. So it's important to recognize that humidity charts give us physical property for a humid air system. It's given to us in a basis of per kilograms of dry air. We'll also look at relative humidity. In this problem, we know that there's 100 cubic meters of humid air coming into the heater per minute. It's entering at 20 degrees C and a relative humidity of 60%. We want to calculate the heat that is required to heat the air to 40 degrees C. That's shown in the flow chart below. On the inlet side, we know the volumetric flow rate, the temperature, and the relative humidity, and we know the outlet is at 40 degrees C, and we want to find Q. Anytime we're trying to calculate a heat, we need an energy balance. So for our open system, our energy balance reduces to Q is equal to delta H. The humidity charts provide specific enthalpy on a per kilogram of dry air basis. So with that information, we can rewrite our energy balance as Q is equal to the mass flow rate of dry air times the change in specific enthalpy, which is given to us in a per kilogram of dry air basis. So we need to calculate two parameters in this case, the mass flow rate of dry air as well as the change in specific enthalpy. And we can look at the humidity charts to help us with both. First, we'll use the humidity charts to help us find the change in specific enthalpy, which by definition is the specific enthalpy at the outlet minus that at the inlet. To find a position on the humidity chart, we need at least two pieces of information, and we know two at the inlet. We know the air going into the heater is 20 degrees C, and we can find the temperature along the x-axis of the humidity chart. Here it's labeled specifically dry bulb temperature, which represents the temperature that we're used to thinking about, the temperature that you can measure with a thermometer. So the inlet air is 20 degrees C. We also know the relative humidity, which can be found on the curve sweeping across the humidity chart. We know that the relative humidity of the inlet air is 60%. In other words, the air is carrying 60% as much water as it could saturation. If we follow the relative humidity curve down the temperature scale to 20 degrees and find the intersection of the 60% relative humidity curve with 20 degrees C, we know that our inlet air is represented at this point on the humidity chart. The first step in calculating the specific enthalpy is finding the enthalpy at saturation, which can be found on the scale in the upper left region of the humidity chart. We get the enthalpy at saturation by following these diagonal curves to the enthalpy scale. The value that I'm going to use from the enthalpy scale at the inlet, specifically at saturation, is 43 kilojoules per kilogram of dry air. Keep in mind that this specifically represents the enthalpy at saturation. We know the inlet air is not saturated, it's only 60% saturated. So we also need to account for the enthalpy deviation, which are the curves that sweep more vertically across the humidity charts. So our inlet condition is somewhere in between these two enthalpy deviation curves of negative 0.1 and negative 0.2 kilojoules per kilogram of dry air. For the enthalpy deviation, I'll use the midpoint of these two curves, which is negative 0.15 kilojoules per kilogram of dry air, which gives us an inlet enthalpy of 42.85 kilojoules per kilogram of dry air. We also need to find the specific enthalpy at the outlet, but the only thing we know about the outlet is that it's 40 degrees C. Minimally, we need two pieces of information to find where we are in the humidity chart. But if we think about what we know about the process, it can help us trace a path along the humidity chart to help us arrive at the outlet condition. We know that there's no water being added or removed from the air, so the absolute humidity, or the moisture content, which is found on the y-axis, is not changing. We're only heating up the humid air. So we know that the moisture content has to stay constant, which implies that although we don't know anything about the relative humidity on the outlet, we do know that the moisture content stays the same and we can move horizontally across the humidity chart until our final condition, or our final temperature, which we know is 40. So our outlet condition is represented by this point on the humidity chart. And if we want to find the specific enthalpy, like we did at the inlet, we can trace this diagonal curve up and left to find the enthalpy at saturation. The enthalpy at saturation that I'll use in this case is 63 kilojoules per kilogram of dry air. Again, the air is not saturated at the outlet. In fact, the relative humidity is going down. As we increase the temperature, the capacity for air to carry water is going up, so the relative humidity goes down. We're approximately 20% relative humidity at the outlet. So again, we need to find the enthalpy deviation for air that is not saturated with water. The two enthalpy deviation curves that are closest in this case are negative 0.6 and negative 0.8. It makes sense that the deviation is larger in this case because we are further removed from saturation. I'm going to use the midpoint in this case, which is negative 0.7, which gives us a specific enthalpy at the outlet of 62.3 kilojoules per kilogram of dry air. If we plug these values in and calculate our change in specific enthalpy from the inlet to the outlet, we get a change of 19.45 kilojoules per kilogram of dry air. Next, we need to find the mass flow rate of dry air, which isn't changing in the process. The mass flow rate of dry air into the heater is the same as the mass flow rate of dry air out of the heater. What we do know is the volumetric flow rate into the heater is 100 meters cubed of humid air per minute. A piece of information that's going to help us on the humidity chart is the humid volume, which gives us the volume of humid air in meters cubed per kilogram of dry air. If we look at the units of the volumetric flow rate in the humid volume, we can see that we can calculate the mass flow rate of dry air by dividing the volumetric flow rate of humid air by the humid volume. Since we know the volumetric flow rate at the inlet, it's important that we find the humid volume at the inlet as well. As the air is heated from the inlet to the outlet, both the volumetric flow rate and humid volume will change. So we need to relate these two quantities at the same point in the process. We know the inlet's 20 degrees C and 60% relative humidity, which is represented by this point on the humidity chart. And we can get the humid volume at this point by looking at the steeper of the set of diagonal curves. And there's only a couple of them. So we're somewhere in between 0.8 and 0.85 meters cubed per kilogram of dry air. So we're pretty close to the 0.85 line. I'll use a value of 0.84 for the humid volume. We can use that value to calculate our mass flow rate of dry air. So we have 100 meters cubed of humid air per minute. And we're dividing that by our humid volume, which we are going to use a value for 0.84 meters cubed of humid air per kilogram of dry air. So when we plug these in, we can see that the units of humid air cancel out, and that gives us a value of 119 kilograms of dry air per minute. If we go back to the beginning of the problem, we can use these two numbers that we got from the humidity charts to solve our energy balance. So again, Q is equal to the mass flow rate of dry air times the change in specific enthalpy given to us in a per kilogram of dry air basis. So using our numbers, Q is equal to 119 kilograms of dry air per minute times our change in specific enthalpy, which is 19.45 kilojoules per kilogram of dry air. So the heat required for this process is 2315 kilojoules per minute.